Hello everyone, welcome to Spark Study. In this video, we'll study about the stability analysis of the linear system. Okay, a system is said to stable if and only if it actually giving the bounded output when there is bounded input. That means you are, let's say you are walking in a road. Suddenly there is a some disturbance in the road or some stop signal in the road, and when you approaches near to the stop signal and the stop signal remove, and you are again continuing straight in that road. Okay, so in that case you are stable. But when you try approaching to traffic and traffic it actually make you stop for some time, then your system is unstable. And if the system, if the traffic try to make you diverted in the other way, then you are unstable now. Okay, that means for certain amount of input, okay, that means you are not changing your input. If you are not changing your input, your system output should not change. That is the stable system. So we can say a linear system is said to be stable if and only if the response is BIBO when the cause is cause is also BIBO. That means your response is bounded output. Okay, bounded input, bounded output. Okay, or you can say the response is bounded, not BIBO. Your response is bounded when the cause is also bounded. So this is called BIBO, or bounded input, bounded output. Okay, and this system is maybe the stability may be two types. We can say the stability is two types. One is absolute stable, and another is relative stable. Okay, so what is absolute stable? Okay, so this relative stable is also called the asymptotic stable or zero input stability. So that what is absolute stable? When you ask whether system is stable or not, the answer is yes or no. If the answer for the question is yes or no, that kind of stability is called as absolute stability. So either the system is stable or the system is unstable, but we have no idea what is the degree of stability. That means up to what time or up to what constraint the system is stable. We do not have any bother about that kind of thing. So that this kind of system is called absolute system, either yes or no, either stable or unstable. But if your systems gives the degree of stability, that means the system 1 is little bit more stable than that of system 2, or system 2 is little bit less stable than that of system 1, that kind of stability is called as relative stability. Clear? So let us come back to the class 7 problem, the train problem. Let's say this is a train traveling from left to right. Okay, do not consider this is actual train, this is the example. From left to right, and you are standing here. The speed of the train, what you observe, that is called absolute speed. Okay, unless the train depart from the platform, the speed is zero. Once the system depart, or once the train depart, the speed increases. Okay, that means unless we have no input, then there is no response from the output. That is stability, that is stable. But if this is one train and this is another train traveling in a parallel path, this is the loco-pilot here, this is the loco-pilot here. So this loco-pilot can see this train is moving, and this loco-pilot can see that this train also moving. So the both the train are moving in the same direction, but with different speed. Okay, so if this speed is more than this speed, we can say this train is relatively slower than this train, or this train is relatively faster than this train. So if in terms of stability, this train is relatively more stable than that of this train, or this train is relatively less stable than that of this train. Clear? So once the system is found to stable, I mean from the yes or no question, if the system is found to stable, that means once you find the absolute stability, then you think about the relative stability. Clear? That means for getting relative stability, you need to analyze whether the system is absolutely stable or not. So the location of poles in the plane give the relative stability. Clear? So if I draw a simple S plane, we know that we do not bother about the poles. If any pole lie right side to the S plane anywhere, then the system is unstable. That means absolute stability. We do not bother about the position of the pole. Right side the pole is the unstable, left side of the pole is stable. Okay, yes or no? We do not bother about the position of the poles. But if the poles is here, then this is stable. If this pole is here, this is more stable than that of this pole. That gives the relative stability. So from this relative stability concept, we can find the maximum overshoot, or we can calculate the maximum overshoot, that is MP. We also can found the damping factor or damping ratio, that is zeta. Then also we can find the gain margin and phase margin. We have not come across these two terms. We'll study these two terms when we study about the Bode plot, polar plot, and Nyquist plot. Then we'll come across these things: gain margin and phase margin. So margin refers to what is, you know what is margin? So excess things, how much excess, that is called margin. So gain margin, that means how much excess we can increase the margin of gain, or how much excess we can increase the gain so that my system becomes stable. That is the excess kind of thing. Okay, let's say you have a notebook whose margin is like this. Okay, so this is your area to write, but this is a margin. If sometimes you can go from this to this, but if you go beyond this or beyond that, then your page over. Okay, so this is the margin, so availability, so that you can use for in future, that is called margin. Clear? So let us recall about some transfer function. From the transfer function, we can find out the poles and the impulse response, and after that we can see the system is stable or unstable. So let's the transfer function is 1 by s, 1 by s plus a, 1 by s plus a. So let the transfer function is 1 by s plus a. So here minus a is the poles. If you draw a j omega axis or s plane, we can see this is the real part, you know that, and this is imaginary. So I am not writing again and again. You understand this thing. So this is minus a. So here you can see the pole is lying left to the j omega axis. So the rest, and it is real value. So if you take the if you convert it into time domain or inverse, take inverse Laplace, then it comes with e to the power minus at. So which response will give like this. Okay, this is t and this is your e to the power minus at, and this is, you know that, after some time this becomes 0. So this is stable system. Okay, but if the transfer function is 1 by, I will write somewhere here, 1 by s minus a, then minus is plus a will be your pole, and it will be somewhere here plus a, and the time domain becomes e to the power at, and the impulse response will becomes like this. And when the time tends to infinite, the system go anywhere, so that the system becomes unstable. Clear this thing? Okay. Similarly, if we, so let's say my transfer function will be 1 by s plus a the whole square plus b square. I will get some imaginary terms, and my pole's location will be somewhere here. So this is will be minus a, and this two will be jb, and this is minus jb. So here I have complex conjugate pole lies in the left hand side of the S plane. So my response will look like this. We can make the response will look like this, and obviously the system is stable. And if my transfer function is just change s minus a the whole square plus b square, so the poles will be this side. So this is a, this is j beta jb, this is minus jb, and the response will go like this. So the systems becomes unstable. Clear about this? So we have studied these things earlier. I'm just making you revise again. Okay, similarly, if you someone ask you the transfer function 1 by s, the pole will be s is equal to 0, that is origin. So I told you, when the system's pole is in origin, then the system is stable systems, and this is the response, stable system. And I told you somewhere in some video, 1 by s means integrator, integration, or in analog electronics you have studied this 1 by s term is integrating, and only s is differentiating, d by dx or d by dt. So if you go for 1 by s square, that means 1 by s square means 1 by s into 1 by s. We can say, if this is my constant, if you can it make you this as integration, we can say integration of 1 by s is called 1 by s square. And we know that always from the signal point of view, in the test signal I told you, integration of step is equal to the ramp signal. So we have studied these things. That means it is very clear that if the system is 1 by s square, that means there is two value of s at origin. So one is here, one is over that. So that more than one poles at origin. So integration of this thing, or integration of the step signal becomes ramp signal. Someone asked me in a question in the previous video or previous lecture, sir, why if one poles at origin gives stable system, if more than one poles at origin not giving stable systems? This is the because if you make you this is constant, if you integrate again and again, that means if you increase the denominator s term, the integration increases, and the integration of step signal is the ramp signal, and this become unstable. So what of this 1 by sq? So this is integration of 1 by s. That means integration of ramp. So integration of 1 by s is the ramp na. So integration of ramp is parabola. Okay, so that means the system response will be like this. Anyhow, so if there is more than one poles at the origin, or we can say if the systems is not type more than type 1 system only, then the system is completely unstable systems. I repeat, unless and until we have only one pole at the origin, that time system is stable. If more than one pole lies at the origin, the systems become unstable. I hope you can clearly understand why the systems becomes unstable if more than one poles located at the origin. Clear? So from the earlier diagram, we have drawn a diagram like this. One pole is here, another pole is here. So this is minus A, this is minus B. The system is 1 by S plus A and 1 by S plus B. Here the response is fast response as because distance is more. Here the response is slow response as because distance is less. So let's say this is system 1 and this is system 2. We know that the less is the settling time, the stability is more. The less in the settling time is equal to the larger distance. So this is less settling time, this is more settling time, this is less distance, this is more distance, so that this is more stable than that of this. So we can say the system 1 is more stable than system 2. Okay, okay. So system 1 is more stable than system 2. Let us consider a diagram like this. I have one pole here, one complex pole over here, another complex pole over here, another pole is real pole over here. So the response of this is more time steady time or more settling time. For this, the time settling time is very less, and for this shall give under damp oscillation with high magnitude, and for this we'll get a undamped response for low magnitude. So that we can see from that this is larger distance than the of this, than that of this, and than that of this. So that we can say this system is more stable than that of these three systems, or this system is more stable than that of this system and this system, but this system is less stable than that of this system. Similarly, this system is less stable than that of these three systems. So this is called a relative stability, so that we can relate the stability with respect to the position of pole. I repeat, the position of poles gives the relative stability, whereas to get the absolute stability we need to know whether the poles are in the right side or the left side. We do not bother about the location or position of the poles. We just give the answer if the poles are the right side, it is absolute unstable. If the poles are in the left side, it is absolute stable. once we found the absolute stability, then we can think about the relative stability. Thank you very much.